Good morning or good afternoon, everyone, depending on where you're joining us from, and welcome to today's webinar. My name is Sam Moulton from the Business Review, and I will be your host. It's our pleasure to have Olympus with us today, who will be discussing diverse uses of advanced ultrasonic inspection technologies for pipeline manufacturing, construction, and maintenance. Today's guest speaker is Nicholas Bublitz, Global Product Support Specialist. I'd like to welcome you all to our webinar platform On24. You'll notice that this webinar is browser-based, so if you disconnect at any point, please click on the link you receive via email to rejoin. In order to ask questions, you can send them in via the Q&A widget at the bottom of your screen, or use the questions box, which is at the top left-hand corner. We'll allocate around 10 or 15 minutes at the end of the session to try and address any of your questions or thoughts. If you click on the green resources widget, you'll find some links from our speakers to view. And if you require help at any point, please click on the yellow help widget. But now, without further ado, please allow me to welcome Nicholas. Nicholas, over to you.
Thanks, Sam. I also want to echo the welcome Sam put off on behalf of Olympus. We know it can be quite hectic to join these live events, but hopefully you enjoy it. So we have about 45 minutes for the main content, and we, as you can tell by the title, have a pretty diverse, broad subject matter. So the real goal here will be to give some basic introduction information about all the different levels where advanced ultrasonic equipment is used along the pipeline manufacturing, construction, and maintenance process, and then pique your interest. And there's plenty of other resources that we can go to for more in-depth information. So without further ado, we'll go ahead and get started. So we look first just to give everybody kind of a very basic understanding of basic ultrasonics, because we have a very diverse crowd of different knowledge bases, I'm sure. Basically, ultrasonic theory, we usually take electronical energy, convert it into sound energy, and then look for flaws or do wall thickness measurement inside of a piece. Typically, in most industrial applications, that's done in a pulse echo type matter, where we're sending sound at a particular angle. It's reflecting off an impedance mismatch, which could be a crack, lack of fusion in a weld. It could be the backside of a wall trying to measure the thickness or look for corrosion. And typically with ultrasonic techniques, conventionally we use just one typical angle. That might be a 0 degree, as pictured here in the very top, where we're looking for wall thickness or corrosion. Or it might be put onto a ultrasonic wedge or shoe, where we can actually generate an angle. But the basic properties are the same, usually with two different types of waves, longitudinal or shear wave. More different types of wave exist, but for most of our industrial NDT applications, this is usually what we use in the field. The whole principle really works on the idea that we get the best reaction from flaws or a back wall or a corrosion cell when the ultrasound impinges on the defect or the material at a 90-degree angle. So as we start to deviate from this, we might get less of an amplitude response or less of an echo back, and in some cases, if a flaw is highly oriented away from whatever angle we choose in ultrasonics, we might get no response. So we can see with only one angle, we're really limited to what we can do. Typically for weld inspection, throughout the years, we've kind of looked at the general weld geometries. There's been some common angles that have been chosen, like 45, 60, and 70, where we can actually just screw on a different mechanical shoe. And that allows us the physical properties to generate at whatever given angle is going to give us the best test. Typically what we get out of a conventional ultrasonic system is basically, as we see here in the bottom picture, it's just an amplitude response and what we call an A-scan. Different ways to display this on a gauge, but typically with this we'll be able to get our amplitude response to determine the severity and also do some general sizing. Different techniques exist to be able to tell the depth. But unless we're doing a very high-end mechanical system, there's a lot of mechanics and full automation, we don't have a lot of good picture or representation of the flaw. It's really based upon the person doing the ultrasonic test to interpret that, try to characterize the defect by the echo dynamics seen in the A scan, and then use some gates and other things on the gauge to determine the depth and report it. So it can be very limited in some applications. It's just, like I said, really up to how well the person's been trained and his experience in the field. So we go a little bit further. One of the things that Olympus NDT does is we produce several levels of advanced ultrasonics. So we just kind of define that first. What is it? Well, we looked at what conventional ultrasound is. Generally, when we're talking about, for this webinar and in general for the industry, when we talk about advanced ultrasonics, we're really talking about phased array ultrasonics, time of flight diffraction. We include guided wave, which is sometimes referred to as long range UT, and then just automated ultrasonics in general, where we're using encoders and then all the way up to fully automated inline systems. And if we look at just categorizing this for its use for pipelines, we can see that these different advanced ultrasonic technologies are really used at all different stages of a pipe, from the time it's being fabricated, manufactured by the person responsible for making the pipe. Once we go to actually install the pipeline, whether onshore or offshore. And then as that pipe ages, obviously different damage mechanisms can exist or corrosion could occur. So during maintenance of the pipeline, we're also using these advanced ultrasonic techniques. So exactly what is phased array? For many people in the NDT industry, it's still fairly new. Olympus has been doing it for about 20 years now, but with any emerging technology, it always takes quite a bit of time for the people to accept it, the codes to accept it. It's really become very popular in the last 5 or so years. We're seeing a huge amount of use in the pipeline and other industries. It really developed from the medical ultrasound. So you can imagine the scans of the baby or the other medical imaging we do with ultrasound. It's taken from that general concept and just applied in an industrial way. So basically what we do is, instead of having a single ultrasonic crystal like we would with conventional ultrasonic testing, we basically group many different elements and put them into a single housing, as we can see here. Typically those are varied from 16 to 128, but throughout the history, and some very complex arrays for more scientific or in-depth testing, arrays have been made with over 1,000 different individual elements. Some people familiar with NDT might think of paintbrush transducers, a little bit different concept. Instead of just physically putting probes next to each other, we actually have each one of these individually wired and have the ability to control them in groups instead of being isolated individual elements. So it's really the core is the phased array probe, along with some software that allows us to do some very interesting things. We talked about angles. We'll look at it in the next slides as well. But instead of being able to be limited to the single angle of whatever wedge we put on, we can actually change that angle by manipulating individual elements and groups of elements. We can actually focus the beam to certain areas within some limitations. And we can also kind of mimic physical movement that we would normally have to do by hand by electronically rastering a single fixed angle through the transducer. So really the goal here is, and we'll look at some of the benefits as we go, but really compared to conventional UT, we can improve the coverage, defect characterization, ability to detect different damage mechanisms, and then improve sizing. So we're making the right call and we're not doing unnecessary repairs. On the bottom of the screen there, you can see for industrial uses, 2 of the basic ways that we use phased array. It's really a sector scan or multiple angle, or instead of having that single beam hitting the weld that we saw on the previous slide, here we have, say, a shear wave scan of, say, 35 to 70 degrees, where we can just put the probe in a single position, cover the entire weld very well. And then on the right-hand side, it's what we call a linear or electronic scan. So here we've chosen a single angle, in this case maybe 45 degrees instead of the single 45-degree beam. And we're electronically rastering the ultrasound through the entire probe in order to get a better coverage without moving the probe. Just go kind of more of a visual way to see how does this all work. We're talking about conventional UT, besides some basic electronic manufacturing. We're really talking about just being a slave to physics. So we send electrical engineering in, we excite a crystal, and basically whatever wedge we put on, based on a theory called Snell's Law, we're just going to get that angle out. There's not much control we can do besides the physical hardware that we put onto the ultrasonic gauge. So in this case, we're just showing a very simple 0-degree pulse. If we hit something, we get a reflection back and a scan on top of our screen. So really all phased array is, all the ultrasonic principles are basically the same. We don't really defy anything. And in fact, all the individual A scans that we see are basically the same as a conventional A scan. We just combine physics with software and try to exploit ultrasound to the best practical use of it possible, if you will. So the phased array transducer, we have many different elements all lined up into a single case, individually wired. And we control the different delays to basically form different wavelets that will form together, and using the principle of constructive interference, deconstructive interference, we can actually manipulate that angle. So here we have a flat probe. If we just fired it like a conventional probe, we just get that 1 0-degree beam. But if we start to control those elements a little bit differently and use constructive interference, we can see that we can get, a whole sweep of angles. Very commonly with a flat transducer, we can generate from, say, -30 to 30 degrees. On a shear wave wedge for typical industrial weld inspection, we're going to look at 35 to 70 degree shear wave and beyond, but that's a very typical scenario. So we're able to do this at a very fast rate, in the nanosecond rate, so we can actually do this real time, which has a huge benefit to be able to do all these inspections very quickly. The other type of thing we can do most commonly is the electronic raster, where if I was taking a 0-degree probe, inspecting the wall of a pipe, say, for delamination, I would have to physically move that 1-inch or half-inch probe over every little part of that to see if there was any delamination or other defect. Here we have maybe a 2-inch long probe, and we can have the electronics do some level of rastering for us. So we can do very quickly 49, 50 beams in a single probe and just increase our coverage and detection capability. A little bit step further, so when we talk about phased array for welded pipe, it really happens along all of those stages that we talked about for pipeline. It can happen during the manufacturing stage, the construction, as well as the maintenance. And there's actually a lot of different ways that we use it. If we kind of break it down into some basic categories, we're talking either manual or encoded, and we'll go more in depth about encoded a little bit later. But manual will apply that test very similar to how we would do a conventional flaw detector weld inspection, where the probe is still manipulated back and forth, but with phased array imaging and some of the other tools, we have just a much better test to look at. So in the top right-hand picture, we have a typical portable phased array unit, where instead of just that single A scan that we saw on the conventional gauge, now we have what's called a sector scan with a shear wave of 35 to about 70 degrees. We can actually put a weld overlay so that we can see the profile of the weld to help us characterize and position defects, as well as make the reporting clear for all the people that need to understand what's going on within the weld. Also a possibility of doing ray tracing, where the defect is actually physically located as we position the flaw, either on the bevel line or in the root or into the base metal. So it helps add a lot of tools for the operator to help characterize and correctly identify the defect and the extent of the defect. One of the big benefits is we still have all those A scans, so it's like having 35 conventional flaw guys out there inspecting with all the different angle between 35 to 70. We're just putting it all into one collective image, and it's really the power of being able to look at all that information in one snapshot and then manipulate it to gives us the power of the phased array for weld inspection. So this is really especially helpful for characterization of unique damage mechanisms that are hard for a normal operator to understand. Things like hydrogen-induced cracking, stress corrosion cracking, just cracking itself, where we might have very branched cracks. Being able to take a big slice of information versus a single A scan at a time is very, very powerful. So really we're looking for better detection and sizing, as well as improved coverage, better reporting as well. If we look at encoded weld scanning, it's a little bit different. So when we talk about encoding, all we're really saying is we're adding a small device, often a wheel, that's going to record our position in relation to the ultrasonic data that we're taking. So what you hear, as you show on the top, is a fully automated scanner. So this is motor controlled. It's going to be push button, be able to go around the circumference of a pipe and record, in this case, both phased array and TOF data. We'll talk about TOF data in the preceding slides after we introduce phased array. Or we might have just a semi-automatic. So semi-automatic meaning it's encoded. We're going to record the linear movement of it and attach that to our data, but it has to be physically moved by the operator. So obviously a lower cost type scenario, and both can be practically applied. So this one's made for tanks where we can actually adjust it. It could be applied to pipe as well, and we actually have different places we can place our sensors. Then we have special ones made specifically for pipe. So this is a chain-based scanner that can go from about 1.75 up to 38-inch pipe or beyond. And we just have different links that allow us to position the sensors correctly around a pipe and do a very accurate scan. Go back one slide. We can actually look at what encoded data, what the real benefit is then. We can start using advanced features like multi-group, where we can inspect from both sides of the pipe as well and get both that data all at once. But we have a linear representation of that data. So things like defect length, all of a sudden are 100% their actual length versus having to do a manual sizing technique. We're able to manipulate this data because it's a digital record, and we're also able to keep it for archiving and auditing purposes. So really when we talk about encoded weld scanning, generally we're talking about phased array here, but often advanced ultrasonic techniques are combined. So in the bottom here, it's actually different techniques that we often use together inside of our encoded scanner. So it might be just phased array from both sides of the weld. It might be phased array along with TOF. It might just be more conventional pulse echo conventional angle sensors along with TOF, or we could do multiple groups of TOF. So it's really a varied ways that we can adapt the ultrasound to whatever we need to be doing. So to a little bit more about the imaging and why it's so useful. If you think about just having that amplitude response or that single A scan, and as the operator of a conventional unit moves that, he basically has to try to keep a track in his mind based on his training and his experience. It can be a big difference between one operator and another. Here we have shown a typical S-scan or sector scan image of a phased array of a weld. So we have a weld overlay that we can actually design in the actual weld profile, which will be a huge benefit in positioning and correctly characterizing the flaw. We have centerline markers. We have leg skips where we can actually see the top and bottom of the component. And then as we can see here, when we see a flaw, it's going to line up correctly based on its positioning to the sensor. So really what we're doing here is we're giving 35 to 40 times more information than that single A scan and putting it together in a representative way that the guy doesn't have to try to understand many different single bits of information. So it's a very powerful tool. It gets even more powerful, some of those hard to characterize damage mechanisms that are branching, stress corrosion cracking, hydrogen-induced cracking. These type of things are somewhat easy to say, hey, we have a problem, but it's really hard to characterize it, how bad the problem is. What's the deepest crack? What's the highest branch that's coming out of a crack? Because just looking at an A scan, that can be a very tough thing to do. The bottom is another showcase of that. We actually have some phased array images from hydrogen-induced cracking. So this again, the conventional transducer, we might be able to say it's there, but having to do many long time of scanning to try to figure out what's the deepest branch, how serious is it, or do I just have laminations, or are there's laminations connected where I have like a side step cracking that's connecting them, which is much more severe as far as for the pipe or whatever we're testing. So with the phased array image, we're actually going to be able to grab a huge section of that base material and see very clearly whether they're separate laminations or indeed we have cracking that is connecting them. So it really provides all that extra information to make the right characterization. One of the huge ways that we've seen phased array become really popular in the last couple of years is to replace or augment radiography. People really like radiography in general because it provides a picture that they're familiar with. Anybody can look at a black and white radiograph, and even if they're up the chain a little bit, maybe they don't know how the technique works, they can see the weld and the flaw represented in something that they understand. Conventional UT doesn't really have this. You know, you're taking the word that somebody has the right training, they're making the right call, they're saying you have a crack, but all they have is an A scan. It doesn't really look like a crack, and you can't really visualize the weld. So one of the reasons phased array has helped that along is that it does actually provide images, side views of the weld, as well as top-down views that once we merge the data, it can actually look exactly like a radiograph. So it's a way to use ultrasound to provide people the comfort that they have with radiography without some of the inherent disadvantages or potential disadvantages of using radiographic techniques. From a physics standpoint, ultrasound in general and phased array, advanced phased array and TOFD, if you look at most of the probability detection studies out there, generally will score higher in most trials done between the two for welded pipeline. From a physics standpoint, ultrasound does detect linear defects like lack of fusion and cracks better than a radiographic technique, where radiography has a slight advantage for rounded defects like porosity, slag, this kind of thing. Also what it does is allows us to use fracture mechanics or engineering critical assessment because we really have a third dimension with ultrasound. We're able to very accurately measure the height of the defect. So often with radiography, if we take a normal shot, we have a length. We really don't have a depth of that defect, or we don't have the through-wall height. So really we're based on a workmanship criteria saying, well, this is a weld. In general, good workmanship of the weld would suggest that we shouldn't have a flaw longer than this. So we identify the flaw, and then we have acceptance criteria generally based on the length. As soon as we have the ability to size in the through-wall height or the vertical plane, it really allows us to expand our acceptance criteria, because if we know how the pipe was manufactured down to the engineering level, we might be able to allow much larger defects than what we normally would by just knowing the length and the type of defects. So in the example here, just taken out of API 1104, I know the infographic on this one can be a little difficult to see. But if we had an incomplete fusion and we only knew the length, what's called the standard clause using, say, radiography, as soon as that length exceeded 2 inches, we'd have to reject that. But if we're able to measure the height, which is the far two right-hand columns, and we knew that defect only had a height between 0 and 0.075, or about 2 millimeters, we could actually allow a lack of fusion almost up to 17 inches, 16.8 inches long, because we knew something of that minute height would never have any critical damage or prone to rupture based on how that pipe was designed. Another huge benefit, obviously, is there's no radiation involved with ultrasound, no extra licensing, generally no extra chemicals besides some basic couplant that's safe to handle. So we can generally work right around anything that's going around us. So in a manufacturing setting, we don't have to move to an X-ray booth. We don't have to do it at night. We don't have to move everybody out of the area for danger of radiation. And all the way along 10, too, for constructing a pipeline, we can follow right behind all the other processes that are happening with no concern about any safety hazards. Also instant evaluation. So if we do a scan with ultrasound, the analysis data is immediately available, and especially welds that have no defects, qualified operator can make that call very quickly. If we go do a repair, we can immediately put just a manual phased array probe on it and tell if that repair was good. So we have really instant evaluation and feedback provided. There's no film to be processed that might take days if we take a bunch of radiographs of a weld. The data is instant. As soon as we scan with ultrasound, the data is instantly available. So it can be highly beneficial. So I'm going to turn it back over to Sam just for a minute to conduct a short poll.
Thank you very much, Nicholas. So yeah, it's time for the poll that we're running in today's session. If you could please select the answer relevant to you, just click on the circle and then click submit. And today's polling question and answers are, it's a simple one, are you using radiography? And the answers are yes or no. So Nicholas, if you could just sort of talk around this question in order to give the attendees a little longer to vote here.
Sure. Yeah, in general, we're just trying to look for the people attending today. How many people are using radiography today? One thing that we've been able to do is find those unique instances where we can use ultrasonic in lieu of radiography. Further in the presentation, we'll go into a little bit more detail, but there's a lot of cases that ultrasound is not a good replacement just because of some general properties of the test that needs to be done. But in a lot of cases, we're finding more and more people are looking to, for different reasons, whether it be for operation safely or because of increased regulation and safety hazards, or just improving the process and saving costs. They're trying to find ways that they can either completely or maybe partially reduce the amount of radiography they're using today.
Okay, thank you very much, Nicholas. I think we've got a good number of votes in now from the attendees, so I'll move us on to the next slide and display those results. And yeah, it's pretty conclusive. No has got the majority there with 61.5%. So if you could just comment on that result before carrying on with your presentation.
Sure. No, it's not. I know we have a very diverse audience with us today, so there might not be for some of you a need to use radiography, or some of you might not be using any NDT at all. But there still is, especially for pipelines, quite a big amount of radiography being done out there. In most cases, for pipeline itself, for pipeline construction, there's not too many limitations to replace it with ultrasound. What we find is people generally don't want to do it because radiography is what they know. The people that need to see the images are used to the images. And then actually there's obviously a process under most codes, under ASME, API, the other regulating bodies, that if the code says historically we use radiography, we must actually go through a certain process and show that ultrasound can be performed in lieu of radiography. So that also means new procedures, new training when we change techniques. So there's still a lot of work, but we see this number going up each day. So we'll kind of switch gears. I know that's a very basic introduction to phased array for welds, for pipeline. We're going to switch gears a little bit to phased array for corrosion. So one of the great things about phased array is its versatility, because we don't control it with the hardware, we control it with the software. So we can actually manipulate the same probe in a myriad, or really an infinite amount of ways, just by telling the software to do something different with that probe. One of the things we've introduced the last couple of years, and it's really gotten a really good hold in the industry, is using phased array for corrosion mapping. Typical ultrasound, we either do point measurements with a thickness gauge. We might grid off an area and take random thickness measurements to kind of get a general idea of how areas of condition concern. Or we might use a fully automatic corrosion mapping scanner using a conventional 0-degree sensor. Moves very rapidly, but it's just one sensor, and we really rely on the fast-moving mechanic in order to be productive. So phased array was a very good candidate to improve this process. So with phased array, as you can see here, we can put this on a manual scanner, cover like a 12-inch grid. We actually encode in both axes, so we're basically painting a complete image of the area that we're going over. Or we can actually put it in a fully automatic scanner. But really all we're doing is, the ability with a phased array probe to generate, say, 50 to 60 beams out of a 2.5-inch probe versus a small 1-inch transducer that can only generate one. So here we have a 64-element probe. In order to improve resolution, we basically use a water wedge concept. So we're going to have better near surface resolution, especially if the surface isn't perfect. We have a sealing gasket here. So we could use just this little buggy if we wanted to for more remote areas, or we can hook it to one of those scanners and do either semi-automatic or fully automatic XY scanning, which is going to be able to show us the entire area scanned. And one of the other benefits besides coverage with phased array probe is really the imaging it provides. So here we have an example of just a test standard or a calibration standard with different side flat bottom holes. On the bottom side, opposite of the side we would test from, simulating ID corrosion. We take the buggy, the phased array probe. Even without a scanner, we can manually create an XY map of this entire plate. So what we get after we're done would be something similar to this, where blue is nominal wall of the pipe, and then all these colors will be different thicknesses that we can digitally manipulate very quickly to find the thinnest points, as well as any characterization of how severe corrosion we're looking for, or wall loss. Very high resolution because of the way we overlap our beams, so we're not relying on mechanics to show that we got full coverage where something went wrong. All these beams are interlaced and overlap so that we know we have a very high data density at every point. We're actually seeing the same location, very tight resolution multiple times. We look at that, then we can take that data and look at it from all different ways once we've collected the data. So we have the same image, but we're looking at it in amplitude response, and then both from two different side views. So this really becomes important when we're trying to make the distinction between a corrosion cell, maybe a mid-wall anomaly, or some of those unique damage mechanisms that we can actually detect when we're looking for corrosion, like HIC and SOHIC, hydrogenated corrosion cracking, anything that might occur while we're doing our normal corrosion mapping. So it really gives us the ability to manipulate that data more than just a single beam and look at it for better characterization of the actual condition. And then we can go there, just a kind of a large image of both a mid-wall anomaly shown here, all the light blue being basically good wall, and then a very big corrosion cell with different pits. And once we have this data, again, we can manipulate the data very quickly because it's all digitally captured. We can look at it in an infinite number of ways. So just kind of an infographic or a visualization of that. So usually if we used a corrosion mapping fully automatic scanner, we would use one pitch catch transducer. Really small footprint, and we rely on the mechanics to move very, very quickly in order to be productive and do a large amount of corrosion scanning. Using the standard phased array corrosion mapping probe, we're generally covering an area of about 2.36 inches, and we actually have probably 49 to 50 beams happening and being overlapped. So each little point has multiple hits, large coverage area at the same time. So you can see that with phased array, we just have relying much more on the many ultrasonic beams versus mechanics to be productive. About 12 times more coverage. So we need to move on just quickly to what is time of flight. So time of flight is a diffraction technique where we send and receive energy from two different transducers, normally straddled over the weld. Since it uses diffracted energy, so instead of relying on energy hitting a flaw and then coming back, we actually just hit the flaw with sound, it vibrates, and then it comes out in all directions. The other main difference is we use time information to be very accurate in our measurements. That can be a huge advantage. So we kind of look at it a little bit closer here. So send, receive. We can use it for flaw detection. So shown here is a normal B-scan grayscale for flaw detection. You can see a few different flaws, top, bottom of the weld. And then also for corrosion assessment. So it's very valuable for this where we might have corrosion occurring near the weld or in the weld root zone or erosion. It's a very rapid technique where we can detect and characterize these very quickly. One of the huge benefits is, unlike pulse echo ultrasonics, it's really not relying on the flaw orientation. As long as we can hit it with energy, we're able to get a good response back and use time to accurately measure it. So for data analysis for both of these, and often they're combined together so that we can actually look at the data together and see which one detects it, which way we want to characterize it. This can be done on the instrument or an offline analysis software. Typically the things we're looking for flaw detection are amplitude, depth, height, and length, as well as making a characterization of the flaw. And then for corrosion, we're usually looking for thickness, remaining wall, and material loss. So really when we talk about portable equipment for phased array and TOF, there's some basic considerations we want to consider. Whether we only want to do manual ultrasonics or we want to be able to do encoded with the use of scanners, what techniques we think we'll use, phased array and or TOF. Multi-group capability, so we have different levels of instruments. Some are only available to do one group or one type of scan at a time, shown on the top right there. Or the other ones where we start wanting to use multi-sensor scanners. We can actually do up to 8 combinations of phased array and TOF together. Very useful when it gets thicker or we have a unique application. We want to do a very good weld inspection. What type of specific scanner may I require to do weld inspection or corrosion mapping? Different probes, wedges, and accessories that are available depending on the material thickness, material type, these type of considerations. And then do I need a post setup and analysis software to assist in my inspection? So we're going to switch gears a little bit just to talk about general phased array for pipe inspection for fabrication. We personally manufacture automated inline inspection solutions for both seamless and welded pipe, along with some ERW pipe systems as well. So these are typically put inside a manufacturing environment in line with some other process so that we can basically very rapidly inspect newly manufactured pipe. Typical, very common API 5L or API CT are the typical governing bodies, but it depends on the manufacturer, of course. So what we have is a very high-speed, high-end version of the phased array system, and we can actually put many of these in parallel. So if you have a unique speed requirement or some testing requirement, and we can actually take what we call our quick scan, which is the basic hardware that we use, and we can actually do other types of NDT like eddy current. So sometimes a manufacturing environment might have need for other NDT techniques. So we can see here we have several phased array sensors on the top right, as well as several units in this picture. Each one of those sensors will typically cover about 120 millimeters at a time. And the great thing of phased array for this application is we can actually just manipulate the software. We're a multi-conventional unit. We'd have to position a single conventional phased or conventional probe in an exact position and rely on the mechanics to make sure that it hits the right spot. And obviously that can be limiting in that if something goes wrong with the mechanics or a very small defect or its orientation might not be detectable. We're able to do a huge amount of overlap, set these sensors up to detect transverse, oblique, longitudinal flaws, so flaws in all directions, as well as do wall thickness and lamination checks very rapidly with a lot of bit of over redundance. So here's a closer up example. So normally the pipe will run at a very high speed. We have a huge amount of degree of freedom built into these water wedges, so that allows if the pipe is slightly out of round from one end to the other, we are able to track that in the software and make adjustment for it. And we can basically design systems built around the needs of whoever needs the system built. Let's get a little bit more visual concept of that. So here we have a very large, usually covers about 120 millimeters per sensor. The heads have just a water wedge concept where we're using water as our kind of coupling mechanism, and just different plates that slide out very quickly to change from one diameter of pipe to another. Pipe's going to rotate very quickly, and we're going to use the electronics to cover a very large area with different phased array scans. Okay, switching gears again as we move forward with our time. Look at it just a little bit for new pipelines. So we're talking generally about new pipelines, either onshore being built, usually for the movement of petroleum, but maybe some other product, as well as offshore. So typically what we're talking about as far as a code standpoint here, onshore is usually governed by API 1104, where the offshore is normally done by DNV standard. And there's some unique things about these. These standards cover a lot more than just pipeline ultrasonic inspection. But really when it comes into pipeline inspection, there's also a third document or code called ASTM E1961. And this is really the one that's kind of unique that makes these more critical and makes them a zonal discrimination type requirement. So depending on the contract, when this standard comes into play in conjunction with these other two, we're really talking about a different type of technique. So unlike the sector scans of phased array and kind of a pulse echo, send the sound out at an angle, watch for it to come back, pipeline joints typically have a very narrow bevel. We can see here like a 5 to 10 degree, very narrow bevel. This makes it very difficult even with advanced phased array because we saw earlier that ultrasound works best when we hit a defect at as near 90 degrees as possible. So when you're talking about a 5-degree bevel, we actually, in order to make sure that we inspect these pipelines correctly, we actually use an altered technique called pitch catch. So we're still using a phased array sensor, but instead we're breaking the weld into individual zones, usually between 1 and 3 millimeters each, depending on the joint design and the contract requirements. And then we're sending a single conventional ultrasound at different angles to each one of these zones. And basically, each one of those zones becomes really its own inspection cell, stripped into a strip chart, where we can get very fast, very rapid data. The key thing for all pipeline inspection is productivity. So we need to make sure the whole process from the equipment to the inspection to the calibration to the reporting is all very quickly so that pipelines can be constructed rapidly. So we use a strip chart, we get some information back, and then we're able to quickly see that there's either flaws we need to identify or nothing at all. So here we use levels of color coding and different heights, different tools within the software to quickly be able to tell if there's anything of concern within the pipe itself. So the typical mechanics have to also be very rugged. So whether it's in a desert, all these pipelines usually are very remote areas, salty offshore environments, very hot deserts, Siberian colds. So it's very ruggedized. It's all boxed up. Here we have the acquisition unit and a motor controller along with a laptop computer, as well as the scanner. So the mechanics become much more important than general phased array as far as positioning, because we're using individual beams that have to hit a very small target on the weld profile. So we actually connect to the same type of band that the automatic welder or CRC Evans type band, very high-end mechanics that are going to hold a very precise position. We don't want the probes to be moving any more than a 1/2 millimeter limit in order to make that technique effective. So here on the opposite side, we actually clamp on very rigidly and put either phased array or phased array and TOFD combinations. We can actually put other carriages attached to that probe for transverse detection and any other requirement unique to the pipe. So we have a strong field experience with this pipeline, and every evolution we just try to make it easier to operate, smaller, more conclusive to the environment it needs to operate. We've inspected millions of welds with the PipeWIZARD, hundreds of units in their field, and it's been approved by pretty much all the major oil companies to be used on the construction of their pipeline. So the pipe, I'll go a little bit faster here because we have nearing the end here as far as getting to time for your guys' questions. So we basically will design the weld in. The software will auto-calculate all the beams. We'll actually run over a calibration block, make some adjustments to make sure each beam is precisely placed. And then when we basically get data back, instead of looking at a color image of all the beams, we'll look at individual strip charts, and the color and the size of the box inside of it will very quickly tell me the positioning on the side of the fusion line as well as its amplitude. So we can make very quick, detailed calls and then go in and do more precise measurement as needed. So our last basic one to go over is really guided wave ultrasonics, which is kind of new for Olympus. This is basically a screening tool. It's used to screen in-service pipes and pipelines over long distances. We call it a screening tool because it's not going to give us an absolute value. We're going to use other ultrasonic or other NDT techniques. It really quantifies, okay, we have something of interest, and it's category 1, 2, 3. We don't get a measurement like 5,000, say, from a corrosion pit. But the really benefits are is that we can put it in the position of the collar in one single area and then do a very long distance of pipeline without excavating it or put scaffolding up for vertical pipe, etc. So really what we can do is use it in a pipeline maintenance environment and really reduce the operating cost involved with NDT. So some of the applications, above ground and buried pipe. So if we only have a certain area, we can actually look at buried pipe from a single location and not have to completely unbury the pipe to get general inspection. If it has some coating or insulated pipe, we're actually able to leave that on, where traditional ultrasonics, we would have to remove that completely. We only might have to remove it depending on where the collar needs to be placed. Corrosion at supports and pipe racks. So we're able to actually shoot down a length of pipe and see if there's corrosion at the supports without removing the supports. And then obviously through-wall pipe, vertical pipe, more of the mechanically hard to get to. You know, we don't want to put up a lot of scaffolding in order to do other types of NDT. We can actually screen from the bottom of, say, a vertical pipe and shoot up the pipe and get a general corrosion screening. So compared to conventional ultrasonics, you know, conventional ultrasonics, even phased array, it's really localized to wherever we have the sensor. With long-range UT or guided wave, we place the sensor at different locations along the pipe, and we're able to cover distances up to about 600 feet, so 300 feet each direction of the sensors. And that's really dependent on a lot of variables, the condition of the pipe. If there's a huge amount of corrosion right there, it obviously won't go so far, the amount of coating, etc. So it all depends, but that's a practical distance that could be covered. So when we talk about it being a screening tool, really what we get back is a certain amount of cross-section. So if we see different size responses, we're able to kind of quantify those as severe, most severe, and in between, but it doesn't give us a value like 1,000s, 2,000s as far as wall loss. You can see here we have two different representations of loss of cross-sectional area. One is really biting into the wall. The other one's more generally long along it. And to guided wave, these are really going to look about the same. Where the one on the left is obviously more severe for the pipe, but we only really get back a thing. So then we need to go to the different points that we see and apply other NDT on top of the guided wave to get that precise measurement and make a call about the safety of the pipeline. But it is equally sensitive to both ID and OD defect. So what are the benefits of screening? Really, we're normally using guided wave to maximize and shorten shutdowns and other inspections by preparing for the NDT work in advance. So if we're able to screen a large number of our pipe and target the areas where NDT is most needed, kind of a risk-based type approach, we're able to prepare for that, say, before a shutdown or in lieu of. Minimize manual labor. So again, we can shoot areas where coatings are present or not have to put up scaffolding, not have to remove 100% of coating, and get a general screening and quantification of how the health of our pipeline is. And then we normally pinpoint those areas, and we can do a much better planning for NDT as far as what needs to be done. So the basic instrument is basically a laptop field unit, an acquisition unit, and then all the bands and probes that are going to go around different diameters of pipe. The one unique thing compared to other versions of ultrasound, it is a couplantless. There's no liquid or anything that's needed between the pipe and the sensors. So you can see a complete unit going out to do one diameter here with the unit in a backpack. So generally the imaging, we do get a nice imaging of the rollout of the entire pipe. We have some advanced focusing tools. We're able to identify features like welds that are 100% around the pipe versus defects that are isolated. And then basically from the imaging, just like very similar to phased array, we're going to break down individual A scans and be able to do full characterization of the raw data as well. So just to kind of wrap up on all the topics, because one of the huge parts is training requirements. Since we have a very broad subject matter, it's very unique kind of for each one, but it's usually dictated by codes. So a lot of time with pipeline, that's API, DNV, ASME possibly, depending on the type of piping, but for pipeline, generally API. Also contract and the other legal requirements. But typically what we do from Olympus is we've partnered for years with official training partners. So not only for ultrasound, But for all their techniques on our website, we have a huge database of about 40 or so companies that we've partnered with that can offer the different levels of training, certification, level 3 services, and in some cases inspection as well. So really for a conclusion, we just took a really basic look at some of the ways that advanced ultrasonics are used, like phased array, time of flight, guided wave, as well as automated ultrasonics in general for pipeline, and really just see that at all levels, all stages of the life of the pipeline, generally what we're trying to do with advanced ultrasound is improve the speed and the quality, increase detection, sizing, and reporting capabilities, improve our characterization of certain damage mechanisms, in some cases replace radiography and conventional ultrasonic methods, reduce mechanics, increase coverage, and then in many cases just solve complex inspection problems with very flexible ways to apply ultrasound, similar to the zone discrimination or just using phased array in general. So with that, I will turn it back over to Sam, and I think we're going to take a look at some questions.
Thank you very much, Nicholas. So yeah, time for the question and answer session now. I'd just like to invite the audience for the last time really to submit their questions. You can do that by typing them into the white box on the top left-hand corner and pressing submit, or if that's down at the moment, just click on the red Q&A widget and you'll get that back up and be able to submit those. We've got plenty in already and only about 10 minutes left, so I'll crack on straight away. The first question I've got is, would you say PAUT can replace 50, 75 or 100% of RT for pipelines?
It's a very good question. It's kind of a hard one to answer, but in general, I don't think it'll ever replace all RT. Generally with phased array for the pipeline, the only joints we're really looking at for the main production scans is the circ welds themselves. So if we have bends, then we have to look at a different approach than the PipeWIZARD. We might have to take a manual scanner or something. If we have different joints with crazy geometry, we can't get the band and the production scanner on. Those are a lot of areas, the tie-ins, where radiography still has a huge place because it's just not practical to be really efficient with ultrasound due to the nature of the pipe shape and complexity. So as far as the circ weld joint, we'd love to see 75% or more. We'd love to see that trend go because it really is a very valuable technique, and in most cases there's no benefit of still using radiography for.
Okay, thank you very much. I'll go straight into the next question. They're asking, what are the drawbacks, or what would stop me using it in day-to-day vessel inspections?
Okay, well, I see some of the limitations that normally people do. The biggest one is implementation. So, you have to figure out the codes, you have to figure out, write new procedures, you have to have trained personnel, all these things. This is the biggest obstacle for advanced ultrasound is people, anything new, right? You have to get used to it and you have to comply with new ways of doing it and the cost that is incurred. So, typically what we need to do is you need to evaluate your business environment and see is there a good potential for it. And then normally what I would recommend is contacting one of our consultant companies or the same companies that are doing the training companies. They have a lot of experience at implementing at different types of manufacturing shops and service shops. They can talk you through some of the advantages, disadvantages. Some of the more generic ways that we see a limitation does require couplant in most cases, so some type of liquid being put on the part. Sometimes that can be hard for people who are doing very high temp. Though we can do high temp ultrasonics, it takes a little bit looking at and seeing how to apply it. The thickness limit, at some point down below around 4 millimeters and getting lower, there can start to be some limitations, though we're pushing that every day. And generally those are the biggest concerns. It's more of an implementation thing and changing the way that we do business and writing all the new work procedures and stuff, along with the associated cost of changing over from one technique to another, generally what we see.
Thank Thank you very much. Next question is it possible to use advanced ultrasonics if we do not have the personnel to train with ultrasonic training?
That's also a very good question. Yeah, so normally, a lot of people generally want to be in control and have in-house personnel at some point. But if you look at different markets, most of the larger markets, they have a huge amount of service companies. So service companies will actually buy the technology, take care of the code requirements, certified training that their personnel need, and you can actually just hire the service to come out and apply advanced ultrasonic techniques. And that happens in a lot of times, especially for manufacturing environments, is they will actually do this on a consultant or a short-term basis while they have the plans to train and hire personnel for a long-term implementation of the technique in-house. So there's all different levels of ways that it's implemented, but contacting a consulting service company that can do it near-term is usually a very good path for many.
Thank you. Next question is, for manufacturing settings, is it possible to configure a system for unique pipe inspection or other components?
Okay, also a very good question. So what we looked at in this presentation was mainly the turnkey build it into my process type system that we would normally make for a pipeline or a pipe manufacturer. But a lot of our instrumentation, we actually also work with integrators. So if you have something that Olympus doesn't offer as a turnkey system, it might be slightly unique. It might be something besides pipe, tube, and billet, which is typically the main turnkey systems that we choose to manufacture. There's a level of our instrumentation and different software that we offer either for people to integrate into their environments or their inspections themselves, or we work with many different operators globally that the key part of their business is basically doing that just for you. So we're kind of the third party. We will offer the equipment to the integrator. They have a contract with you, or they look at your environment and what you need to be done. We give them some tools so they can make a nice, easy software environment, and they will be, usually handle all the mechanics required for an automated system. So there's really a path, whether it just be buying a portable instrument, integration of a product, or a turnkey manufacturing type system.
Thank you. Next question is, can I inspect stainless material with these techniques?
It's a very good question. Actually, we get this quite a bit lately. So, generally a lot of pipeline is carbon steel, and it's pretty easy to predict the ultrasonic properties. We see more and more stainless, along with austenitic. I'll include, cladding, dissimilar metals, a whole kind of group of different engineering alloys that have kind of unique ultrasonic properties. And we just might vary the technique a bit. Different types of wade modes might operate better. We might use some advanced type arrays like dual arrays or matrix arrays that allow us to just inspect these type of materials a little bit better, because they usually have some unique material properties like grain size or random grain size, as well as they can be kind of a mess as far as how they reflect ultrasound at certain interfaces. So normally with these, they're not as cookie cutter. We can't just say, okay, you have carbon steel from this to this, and we can predict very accurately what might happen. We normally want to take a little bit closer, more detailed look, and maybe take some ultrasonic tests to make sure that we can produce a test that can do the inspection very well. For all the normal stainless manufacturing grades, we do offer turnkey systems. It's more when we get into the production and the maintenance environment that we want to maybe do some ultrasonic tests to make sure that we're applying the ultrasound in the best way possible.
Thank you very much. Time for a couple more questions, I think. One of them is, can phased array or TOFD be used on plastic or HDPE pipe?
Okay, so it's another similar kind of material question, but this is actually something that in the pipeline business is becoming very popular. It's very popular for a lot of reasons, but one of them, it's really corrosion resistant, not being made of metal. One thing for us is plastic HDP, they have some unique ultrasonic properties. They can generate ultrasound in them, so we can test them. But HDP itself, which is probably the most predominant one used for pipe, it's very attenuative, so it really slows down ultrasound very quickly, reduces the strength of it. It's also can have a scattering effect, and usually the joint is actually very vertical. It's straight up and down because basically you're pressing under heat two sections of plastic pipe together. Yeah, we actually have some adapted techniques for these using time-of-flight diffraction with some special water wedges that allow for the lower velocity of HDPE, just the acoustics to happen a little bit better. And we've also explored and made some phased array wedges and standard probes to adapt this, and many of the service companies are doing it. One of the limitations we see with this is acceptance criteria. You know, there's really no code or standard that is widely said what size defect is too detrimental. A lot of the testing is still visual and hydrostatic. So it's really that limitation. But I know several of the code bodies are working on establishing some regulated pipeline standards for plastic or HDPE pipe. But yeah, there's some tools out there, and we see it being used more and more each day.
Okay, thank you very much, Nicholas. I think that's about all we've got time for in terms of questions. So we had a lot in, so sorry if we didn't get round to yours. Olympus will have your contact details, and we'll be able to get back in touch with you in due course. But before I wrap up, Nicholas, have you got any final thoughts you want to give to the attendees briefly?
Just another thank you for joining us. I know everybody in this industry is very busy, and hopefully, at least in the short amount of time we had, with a very broad topic range, we piqued your interest in a few things. We have several live or on-demand webinars on our website that speak to each one of these subjects in much more detail, along with some other resources. So either contact us or check out our webpage if you're interested in more details in depth on any of these subjects.
Okay, great. So that just leaves me to thank you again, Nicholas, for a great presentation. To thank Olympus for sponsoring the session. For the attendees, you'll receive an email shortly telling you how you can access the on-demand version of this webinar, or you'll be able to access this through our website, which is www.business-review-webinars.com. We look forward to sharing further webinars with you, so please do keep an eye out on the website I just mentioned. Follow us on Twitter, which is @BRWebinars, and join our LinkedIn group, Business Review Webinars. Once this webinar ends, a survey from Olympus will appear, and we invite you to please fill this out for us. Apart from that, just thank you once again, Nicholas, and I hope you all have a nice day.